Okay, before I talk about the collapse postulate, let me also tell you something interesting. So we assumed that observables are represented by, say, Hermitian / self-adjoint operators. This postulate doesn't seem very, well, to a lot of people, this postulate doesn't seem something very physical. It seems very mathematical in nature. So people have tried to formulate quantum mechanics, which does not need this postulate, okay? It is not the standard interpretation of quantum mechanics, I must warn you. So what people observed is that if the Hamiltonian is PT symmetric, meaning that it's symmetric under parity, meaning that x goes to minus of x, and time reversal, t, sorry, my spelling is not very good today. That t goes to minus t, then in a certain regime, the Hamiltonians give real eigenvalues. Okay, so there is a version of quantum mechanics where it's called a PT symmetric quantum mechanics. Okay.
Is it related to CPT violation?
CPT violation, you know, they involve, PT involve the same symmetries, but I'm not sure if it's related to the PT violation in quantum field theory. Okay. Now, in quantum mechanics, so in quantum field theory, CPT actually cannot be violated. Okay, CPT must be preserved. But that doesn't mean that PT must be preserved or C must be preserved. In fact, in the standard model, you know, these guys, you know, individually are not, well, PT, they are not always preserved. So, you know, that's something that is a experimentally interesting, has a lot of interesting consequences in cosmology and stuff like that. But that has to be dealt with in a quantum field theory and particle physics class, so I won't go into that. But PT symmetric quantum mechanics is slightly different. It's more basic, and Carl Bender is one of the leading people in exploring PT symmetric quantum mechanics. Okay, I just wanted to mention that as a comment. This is not the canonical version of quantum mechanics, so I won't go into that. Okay. So my next topic, the last one, is going to be the collapse postulate. This is also very, it's a slightly or somewhat controversial. Okay. And there are ways to get around it, and I'll mention those as well. So suppose that, you know, we start with the state that I told you before, the wave function, which is a linear combination of the energy eigenstates. And suppose I measure the energy and find that the value is E6. Now, if I measure H again, you know, in a short, you know, within a short time interval, in which that we take care to keep the system isolated, then subsequent measurements will yield the same eigenvalue, which in this case is E6. So what does this mean? That means that my system started, my system starts off in the state psi, and I make a measurement of energy H, and I get the value E6, then my system must be in psi 6. Because if I measure it again, another measurement, also results in E6. So this means that measurement of an observable, collapses the wave function into one of its eigenstates. Okay? So this is the collapse postulate. In this case, what was the probability that the measurement would give me E6? That would be C6 squared, right? That was the probability. But after this, once this measurement has been done, the probability of finding E6 again would be 1. Okay? This is clear? Because this is kind of important. So suppose that, this is psi 1, this is a state space, not our physical. This is psi 2, and our wave function is, say, psi, and I make a measurement, and then what happens, I find that the measurement gives me E2. So that means that the wave function then collapses to E2, psi 2. And after that, if I measure the energy again, I will always find it to be psi 2. If we take care that in between the particle does not interact with this environment. Now, one thing we know about quantum mechanical systems is that they're extremely sensitive to their environment. They interact with the environment very easily, and they get what is known as entangled with their environment. So there is an alternative version of the Collapse postulate where it says that, suppose that you have a state which is the linear combination of two eigenstates, say of energy operator, and you make the measurement of the energy. So your system was propagating in some state psi, but as soon as you make the observation, instead of the system collapsing to either psi 1 or psi 2, the universe splits into two. In one branch of the universe, the system is in state psi 1. Another branch of the universe, the system is in psi 2, such that in the combined universe, it is still in this state. So this is the called the relative. I think it's called a relative.
So many world
state.
hypothesis.
Yeah. It's called the relative state hypothesis. And this was invented by Everett. And later it was called the many world interpretation. By John Wheeler. John Wheeler had a knack for coming up with very catchy names. Black hole, for example, is the name that was coined by John Wheeler. Yeah, so that's a alternative interpretation, but again, that's not the canonical interpretation, and we won't go there in this course. Okay, so I think I'm going to stop here and ask for questions.
Why is our hypothesis more canon than this one? I mean, we don't have any way of proving either of them, right?
Yeah, but this has actually the problem that the many world interpretation seeks to solve. People have argued that it doesn't actually exactly solve them. There are some technical issues about, yeah, so there are some technical issues, and it's really about taste. There's another class of interpretation of quantum mechanics, which is the most popular interpretation. It's also known as shut up and calculate school of thought. And so there is a large group of physicists who say that interpretations don't matter because they all give you the same answer. So shut up and calculate. I am not in that school, but yeah, but that could be. It's more of an Occam's razor. Like if the collapse hypothesis gives you the right answer, why not? But there are obvious problems with the collapse hypothesis, and let me just point out one. Okay. So suppose that you have a pair creation. So when you have a pair creation, so suppose that you have an electron and a positron which were created in pair. So, where the original system which created said this was some two photons merging, they had zero angular momentum, then you can show that such a system, has a state which has 1 and then psi 2. In the state psi 1, the electron is spinning up, and electron is spinning up, and the positron is spinning down. Whereas in the state psi 2, the electron is spinning down, and the positron is spinning up. Okay. So you can show that this is the state that is created as a result of this pair creation. Now suppose that the electron is here in Alice's lab, and the positron is here in Bob's lab. Now, suppose that Alice decides to make a measurement on the spin of the electron. When Alice makes a measurement of the spin of the electron, it must either be up or down. That means Alice collapses the wave function to either this branch or this branch. Now, simultaneously, Bob's wave function must also be collapsed. Now, suppose that Bob makes the measurement slightly after Alice measures the wave function. Then if Alice has measured the wave function to be spin up, Bob will undoubtedly find that his measurement yields spin down, and vice versa, right? So once Alice has done this, Bob has no choice. Now, this has a problem, a certain conflict with special relativity. Can someone tell me what the problem is?
If the particles are far enough apart, you would transmit information faster than the speed of light?
Yes, it can be put in a more sharper way. In some reference frame, Bob and Alice are simultaneous. There's another reference frame in which Alice, makes a measurement before Bob. But there's another reference frame where Bob makes a measurement before Alice. If the two measurements are made, if the two events,
Causality is broken.
if the two measurement events are space-like separated, then it's not possible to say who collapsed the wave function. Now, causality is not broken. And the reason is that suppose that Alice finds her measurement answer, and she wants Bob to know before Bob makes the measurement. But it turns out that, by the time Alice communicates, with Bob, that, Bob cannot, how should I say? Sorry. So the idea is that, even though this electron and this positron, because of their entanglement, the forcing this guy in one state forces this guy in another state, even though that is possible, you cannot use this so-called faster than speed of light collapse to send information from A to B or B to A. Even though, something is happening faster than the speed of light, it is not propagation of information, okay? And therefore, even though people say that quantum mechanics, the collapse postulate, violates the spirit of special relativity, but it does not violate special relativity. Okay? So there are lots of issues with the collapse postulate. And it has to do with what do we mean by the wave function. So some people think that the wave function itself is a fundamental aspect of reality. Other people think that, it's just ontological description of reality. And there are other people who say that it's an incomplete ontological description of reality. There must be another hidden layer which the wave function doesn't capture. So there are all kinds of different schools of thought about the wave function, which is covered in the subject of quantum foundations, which is a very, very fascinating subject. It's kind of abuts on philosophy, and quantum foundation people are as far as you can get from the shut up and calculate school of thought.